Hello everybody. Today we're going to look at interpreting acceleration time graphs. We've already looked at the position time graph where the slope represents the velocity. We have also looked at the velocity time graph where the slope represents the acceleration. The acceleration time graph is a little bit different from both of those, mainly because acceleration is on the y-axis. And yes, there is a typo here. This should say acceleration in meters per second squared. I don't know how that got past me unless I just copied. Yeah, that's what I did. I copied and pasted it and forgot to change the name. So please change the name on the y-axis. Now, when you have an acceleration time graph, of course, time always being independent must go on the x-axis. Acceleration in meters per second squared goes on the y-axis. If there is a change in the acceleration, it will be shown along the y-axis. So that would be your change in acceleration. That would be a non-uniform acceleration, which normally we wouldn't see, but I'm showing you right now just so you'll understand. Remember, the acceleration is the increment by which you're going to increase or decrease your velocity. In this case, the increment of increase or decrease in velocity is itself increasing. Normally, we wouldn't look at that. Normally, it would be the same increment. In other words, if the increment were 12, it would stay 12 for uniform acceleration. But I wanted to show you this just so that you'd understand that there is a difference between uniform and non-uniform acceleration. Now, what about the slope of the graph? Well, if you looked at the slope of the graph, that would be rise over run. That would give you meters per second squared over seconds, which would also be meters per second cubed. That really means nothing in physics. So the slope of the graph means nothing physically. Okay? So strangely enough, this graph, we don't have to worry about the slope, just on the other two. Now, if it is uniform acceleration, that means you will always have a zero slope. So this right here would represent zero acceleration. Zero slope, and therefore constant acceleration, or uniform acceleration, if you will. While this one, the acceleration is increasing, so you could call it non-uniform acceleration, okay? All right, now, the area between the graph line and the x-axis does have physical meaning, just like it did for velocity, but it did not for position time graphs. If we were to look at the area, say I chose this little area right here to look at between 2 and 3 seconds. For this one particular period of time, the area would be basically the change in time times the change in acceleration. Or in this case, if it's uniform acceleration, it's just times the acceleration. Well, that gives you units of meters per second squared times seconds, in which case one of the seconds cancels, and that leaves you with units of meters per second. And what do we know is measured in meters per second? It's velocity. The area between the graph line and the x-axis on an acceleration time graph represents a change in your velocity. The bigger the area, the greater your change in velocity is for that time period. Okay? Kind of interesting, isn't it? So up here, the area between the graph line and the x-axis during a time interval represents the change in velocity. Now, it doesn't represent a particular velocity. It represents a change in velocity, okay? Please understand that. It's not a specific velocity, it's a change in velocity. Okay, let's go to the next page for a minute. Okay, I think you've got a little bit more of this section before we get to single segmented motion and two-body motion. Let's look at these, let's look at these three right here. You have an object at rest. If we have an acceleration time graph, you have increments that you're going to add and increments you're going to subtract. Okay, this is how you know what sign the acceleration has. And these are positive increments, so you're going to add them to whatever your velocity is. These are negative increments, so you're going to subtract them. If you have an object at rest, there is no acceleration. Okay? What about an object moving with constant velocity? Well, on this graph, if you're moving at constant velocity, do you have an acceleration? No. So it looks exactly the same. So if you do have an acceleration versus time graph with zero acceleration, you really still don't know if it's this one or this one because they're the same. So to determine if you were at rest or moving with constant velocity, you would have to have further information, like from a velocity time graph or a position time graph. Okay? An object that is accelerating uniformly would have a non-zero acceleration increment, and as long as it's uniformly, that increment never changes. So you could have a positive value increment that you're adding to your velocity, or you could have a negative value increment that you're subtracting from your velocity. Either one, okay? All right, now that we've looked at that, let's look at one more thing. We have thus far looked at two equations used with linear kinematics. All right? And those equations are the definition for constant velocity, v equals d over t, and the definition for uniform acceleration, vf minus v sub o divided by t. Now, there are two others that we're going to be learning about, but it just dawned on me we need to talk about transposition, so let's do that first, okay? Now, for this, I'm going to get a sheet of paper. Hang on, let me find one. And we're going to look at what that means to transpose on a graph. All right, I've got a piece of paper I can write on. Let's suppose that you had a graph of position versus time. Okay. We're just making a little sketch here. Let's say that your position time graph looked something like this. Okay? Well, I wanted that to line up right there, okay, with this one too, but oh well. Something like this shape. And what we want to do is we want to plot for these same time periods, we want to plot that motion that exists here on a velocity time graph. Let's take a look. Here's positive velocities, here's negative velocities. Okay, for the same time periods, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, need one more, didn't I? For the same time periods, you want to plot what's happening here on here, but you have to take it increments of time at a time, sections at a time, in other words. For example, from 0 to the second time mark right here, the object is doing one specific thing, and that is it's staying at rest. It's not moving because the position isn't changing. So for those first two ticks in time, that's what you draw for the velocity. It's not changing. Then you go to the next ticks in time. Okay, so from 2 to 3 to 4 to 5, you are moving at constant velocity, because it's a constant slope, in the negative direction. Okay, so you have constant velocity, negative direction for these 3 spaces of time. And here they are right here. So here's the negatively directed velocities. And what you would do is you'd find the value of the slope here, whatever that value is. And then you'd find that value over here on your x-axis, whatever it is. And from the second tick in time out to this one, for those 3 sections, you draw constant velocity. Now, sometimes they do this. Oops, sorry, it's not very straight. They draw a straight dotted line down like this to show that it goes from here to here. All right? Then look what happens. We're moving and then we stop. So for this last set of time, we're coming back to the x-axis where the velocity is 0. So we have transposed the motion that's shown by the slope here onto this graph. 0 slope, 0 velocity. Negative slope, negative constant slope, negative constant velocity. 0 slope, 0 velocity. Get it? That's how you transpose a graph. You can go from position to velocity. You can also go from velocity to acceleration. If we come over here and look at an acceleration one, this particular one is not going to be very much, because here you were at rest, here you're at constant velocity. For all of those ticks in time, you have 0 acceleration. So that's the acceleration graph for these two for this motion, and this is the velocity graph for this motion. Okay, that's what you're going to be doing on your assignment tomorrow in class or at home. We're not going to do much more than this right here today, because I am overwhelmed right now and I need a little breathing room. I'm sure you can agree, we kind of all do. So the notes for today is it, and we will practice interpreting motion graphs and doing some transposition tomorrow. Thanks, guys.